Welcome to the third lecture on approximation algorithms. Today we will talk about the Steiner tree problem and to the related multiway cut problem. We will learn what an approximation preserving reduction is and how to use it to solve the Steiner tree and the multiway cut problem. We will start in the first part with the definition of the Steiner tree problem. We are given some graph G on the vertex set V and an edge set E, like this one here. And we additionally have some edge weights, so for every edge we have some function that defines some positive value that is the cost of these edges. The vertices are partitioned into two types of vertices. We have the terminals that are purple or in T, and we have the Steiner vertices which are pink and denoted by S. For example, here we can have 3 terminals and 1 Steiner vertex. Now the question we have is, we want to find a subtree of this graph G that contains all the terminals. So for example, this green subtree here, this is a subtree that contains every vertex in T. It contains these 3 vertices. And it has cost 4, so you can already imagine what else we want to find. We want to find the cheapest one. We want to find this one with the minimum cost among all subtrees that contain all terminals. So in this example, what is the Steiner tree we're looking for? Here we have cost 4, but instead we could just use all these 3 edges with cost 1 that connect the terminals to this one Steiner vertex in the middle. And then we have the optimum solution with cost 3. This is a very general problem. We have no idea how the graph looks like, we have no idea what the edge weights are, so before we do this, we want to look at a more restricted version. That's something that you often do in computer science. You get some general problem, and then you restrict it a bit to something that's easier to solve. And then you start solving the easier problem, and maybe from that you can get a good solution for the general one. So what we want to do here is, instead of looking at the general Steiner tree problem, we want to look at the metric Steiner tree problem. In this variant, we restrict the graph to be complete, so every vertex pair has an edge between them in the graph. And the cost function has to be metric. That means that the triangular formula holds for every pair of edges. So if we have 2 vertices U and W, then the cost between them cannot be more than the cost if we go from U to some other vertex V and then from V to some other vertex W. For example, look at this graph. Is this a complete metric graph? Well, it's not complete because there's no edge between these 2 vertices. And it is not metric because if we look at this edge here, this has cost 3, but I can also go from this vertex to this one by just moving along the 2 edges here on the left. And both of them have cost 1, so there's a shorter path that has only length 2. What about this graph on the right? This graph has the missing edge, and now the cost here is 2, and if we check carefully, we see that the triangular formula holds for every pair of edges, so it is fine. This is a complete and metric graph, and these are the types of graph that we get as the input for metric Steiner tree.